So have you ever wondered, like, what happens when AI gets a hold of these super complicated math problems? The ones mathematicians spend their whole lives trying to figure out?
Yeah, it's pretty mind-blowing.
Well, get this. Today we're diving into AI mathematicians tackling something called Alon's problem.
Oh, that's a fascinating one.
I know, right? We're talking about prime numbers, squares, and then this mysterious set, A, that's got mathematicians all puzzled trying to figure out, like, what its limits are.
It really gets to the heart of some fundamental concepts in number theory.
Okay, so before we get too far down the rabbit hole here, maybe we should like break down what Alon's problem actually is.
Yeah, good idea. It can be a bit intimidating at first glance.
I'll admit, when I first read about it, I was like, wait, what?
Uh-huh, yeah, I get that.
So where do we even begin?
Well, let's start with something called quadratic residues. Imagine squaring all the whole numbers from 1 up to, say, 10.
Okay, so 1, 4, 9, 16, and so on. Got it.
Now, imagine dividing each of those squares by a prime number. Let's use 7 as an example.
All right, so we're dividing all those squares by 7. I'm following.
You'll notice some interesting patterns in the remainder.
Oh, like some will divide evenly and some won't.
Exactly. Some numbers, when squared and divided by 7, will leave no remainder at all. And those special numbers, those are our quadratic residues.
So it's like finding the perfect fit.
Yeah.
Those squares that divide perfectly with nothing left over.
Perfect analogy. Now let's bring in set A, a set of numbers. Alon's problem asks us to prove that if the difference between any two numbers in the set is always one of those quadratic residues, except for 0, of course, then set A can't be infinitely large. It has a limit.
So it's like this set has to follow these very specific rules, and because of those rules, there's a cap on how big it can get.
Precisely. And that notation you might come across, AAUO 0.
Yeah, that looked a bit scary.
It's just the fancy way of saying that if you subtract any two numbers from set A, the result will always be a quadratic residue, except when you're subtracting a number from itself.
Okay, that makes more sense now. But why is finding this limit, this upper bound, on the size of set A such a big deal? What makes Alon's problem so intriguing to mathematicians?
It's a great question. It's not just about solving a puzzle, it's about uncovering something fundamental about the structure of numbers and sets.
Like it gives us a deeper understanding of how these concepts are connected.
Exactly. And you know what's even more fascinating? We now have AI stepping onto the scene to try and crack this problem.
Like AI mathematicians.
Oh, yeah.
Yeah, that's wild. I can't even imagine how AI would approach something like this.
Well, you're in for a treat because the way these AI go about it is quite surprising. Before we jump into that, though, let's introduce a tool that both AI and human mathematicians use when working with these kinds of problems, the Legendre symbol.
The Legendre symbol. Sounds a bit like something out of a spy movie. What is that, some kind of secret code?
In a way, it is. It's this handy function that tells us whether a number is a quadratic residue or not, without us actually having to calculate all those squares and remainders.
Ah, so it's a shortcut. Like it tells us if a number belongs to that perfectly divisible by our prime club.
You got it. And it's also essential when working with something called congruences.
Congruences, huh? Okay, now those sound a bit intimidating. Are we talking like advanced calculus here?
Not quite. It's really a way of looking at numbers in a cyclical way.
Cyclical, like a clock.
Exactly. Think about a clock. The hour hand keeps coming back to the same positions even though time keeps moving forward. Congruences are kind of similar.
So instead of just looking at the exact values, we're looking at which numbers kind of land in the same spot after we divide by our special prime number.
You got it. It's all about those remainders again. If two numbers have the same remainder after being divided by another number, we say they are congruent to each other.
Okay, that makes sense. So it's a different way of seeing how numbers are related to each other, not just what their individual values are.
Exactly. And this idea of congruences will be key as we explore how AI mathematicians took on Alon's problem.
Okay, I think I'm ready to meet these AI brainiacs. Who are these mathematical masterminds?
Meet Grok and DeepSeek. These are our AI mathematicians attempting to prove Alon's problem.
Grok and DeepSeek.
Yeah, pretty cool names, right?
Definitely. And what did they do?
Well, the remarkable thing is that they didn't follow the typical well-trodden paths that a human mathematician might take.
Really?
Yeah, they went off-road and the results are truly fascinating.
Okay, I've got to know, what kind of unconventional routes did these AI take? Did they, like, invent their own math?
Well, not exactly invent, but they certainly applied existing math in incredibly creative ways.
Okay, I'm all ears. Tell me more.
Let's start with Grok. It used a principle called the pigeonhole principle. Sounds deceptively simple, but it's incredibly powerful when applied correctly.
The pigeonhole principle. All right, color me intrigued. What's this all about?
Imagine you have a bunch of pigeons and a set of pigeonholes where they can roost. The pigeonhole principle simply states that if you have more pigeons than pigeonholes, then at least two pigeons must share the same pigeonhole.
Okay, yeah, that makes sense. It's like trying to fit 10 square pegs into 9 round holes. Something's got to give. But how does this seemingly simple idea relate to something as complex as Alon's problem?
Well, that's the genius of Grok's approach. We'll get into the specifics in a moment, but the core idea is to cleverly assign the elements of set A as our pigeons and the possible quadratic residues as our pigeonholes.
Ah, I see where this is going. If set A gets too big, we're going to run out of pigeonholes for our pigeons, right?
Exactly. And that's where the magic happens. We'll explore how that leads to a solution in just a bit.
I'm curious, what about DeepSeek? What kind of mathematical sorcery did it employ?
DeepSeek took a different but equally fascinating path. It utilized the Cauchy-Schwarz inequality.
The Cauchy-Schwarz inequality.
Yeah. It might sound a bit intimidating, but at its core, it's a tool that lets us compare the sizes of different sets of numbers.
Okay, so like we're comparing our mysterious set A to the set of all possible quadratic residues.
Precisely. And by cleverly using this inequality, DeepSeek was able to demonstrate that set A can't grow arbitrarily large. It has to stay within certain bounds.
Wow, so we've got these two AI mathematicians, both taking radically different approaches, yet both aiming to prove the same thing.